All right. Well, we're all here, I guess. Those of us who are not in foreign countries already. So today what we're going to focus our attention on is the normal distribution. Now, I think our best bet as far as the Excel goes is to save it until we're all together again in person a week from Tuesday. So today, again, we'll focus our attention on the calculators instead of Excel. So that way, when we get back, we can do all the Excel all at once and learn all the commands. In the meantime, we're going to go back and revisit what we discussed about the normal distribution on Tuesday. And if there's time, maybe at least take a look at the exponential distribution, which is the last distribution that we'll be covering in chapter 6. Then when we get back, we'll continue working with that. And then at some point, we have to start thinking about the second midterm. It's hard to believe, but already we're done with the material for the second midterm, which is chapters 4 and 5. So we'll figure that out when we get back. Right now, why don't we just focus all of our attention on the normal distribution? And hopefully you have a calculator with you because we'll be using them quite a bit today. So let me just open up this document that I've created for today, and I'll be posting it on the Blackboard later on. And also, of course, chapter 6. And so we're going to go back and revisit what we were doing. And so you know that we started the normal distribution. And so I just want to quickly review some of its key characteristics, and then we'll do some calculations. All right, so here's the bell-shaped curve that we're so familiar with now. This is a drawing of the normal distribution. That horrific looking function we saw last time, this one, when it is illustrated on a graph, this is what it ends up looking like. And it has all the key properties that we need. We know that the area under the curve is exactly equal to 1 because it is, after all, a probability distribution. We also can see from the graph that it is symmetrical about the mean, and that will help us do some of our probability calculations. Then we also know that it's continuous, and that's because it has an infinite number of possible values. And so, as I mentioned last time, when that's the case, we can't really use a histogram to illustrate it. Instead, we use curves. Okay, and then finally, the two numbers that we need to pay close attention to are the mean and the standard deviation. Let me move this over here just to make some space for me. So yes, the two things we need to know to uniquely characterize the normal distribution are the mean, which you see is designated by the Greek letter mu, and the standard deviation, which is designated by the Greek letter sigma. All right. Now, also, we mentioned on Tuesday that there is one special case that we need to be familiar with, and that is the so-called standard normal distribution. And what separates it from the others is that the mean is 0 and the standard deviation is 1. Okay, now, if you have any experience using charts to calculate normal probabilities, let's say in high school you were briefly introduced to statistics, they probably would have tried to show you at least a little bit about the normal distribution. And if they did, they would have probably had you use tables to calculate the probabilities. So the tables in the back of any statistical textbook are actually based on the standard normal distribution. For other types of normal distributions, you would have to make a conversion in order to use these tables. Now, for us, since we have this wonderful, powerful TI-84, we don't really need the tables, but some people actually prefer the tables. And so when the test comes around for this material, I usually bring a few with me just in case somebody actually wants one. So if you like the tables, you can use the tables, all right? I just want to mention that. Otherwise, it's probably easier if you just simply use the calculator. All right, so we'll start with a simple example. So we remember last time we were getting some practice with calculating probabilities. So first things first, I would quickly remind you that the letter Z is used to indicate the standard normal distribution. So you see in this example here, I'm asking for the probability that Z is between 1 and 2. So the fact that I'm calling it Z means that this is the standard normal distribution. I'm going to make a note of that here. Z indicates that this is the standard normal distribution. So in the problem itself, they're not going to necessarily tell you what the mean and standard deviation are because it's understood that since this is the normal distribution, the mean is 0 and the standard deviation is 1. Okay, so I just want to mention that right now. So like when you're doing the mind tap problems, you may run into the same situation. It'll say, well, here we have the normal distribution. And you're saying, well, where's the mean and the standard deviation? No, you don't have to be told. It's understood that this refers to the standard normal with the mean of 0 and the standard deviation of 1. Great. So this graph shows us what we're trying to accomplish. You can see that we're looking for the area between 1 and 2. And of course, with the uniform distribution, doing this was very simple. We were just calculating probabilities under a rectangle. Of course, that's not the case here. So instead, we have to use our calculators. So if you remember on the TI-84, you start by hitting second vars. And remember, second vars will bring you to a menu of probability distributions. And there's quite a few if you look at it very carefully. We're going to use many of these. By the time stats 2 is over, you'll have used pretty much all of these. Okay, but for now, we're just getting started. We're going to start with number 2, normal CDF. Now, by the way, I do want to mention it. You'll probably notice in this list of distributions, there's also number 1, normal PDF. We will not be using that one in this class. All right, so in other words, never use normal PDF. Now, luckily for us, if you accidentally start to use it by mistake, you'll notice that it's not asking for the information that you're expecting. So in other words, you'll look at it and say, what's going on here? I don't recognize what it's doing. And that's because it's the wrong command. So instead, we'll use normal CDF. And so when you do use normal CDF, you need to tell the calculator 4 things. We need the lower limit, the upper limit, the mean, and the standard deviation. So for any interval, this would be my lower limit. And this, of course, would be the upper limit. So you notice how I put in here 1 and 2. Now, as far as the mean and standard deviation are concerned, because this is the standard normal distribution, that means we're going to put in a 0 and a 1. All right, well, I've already spoiled the surprise for you, but if you type this into your calculator, you'll see that the correct answer is 0.1359 when rounded to 4 places. All right, so you can see from this graph, that means the shaded region has an area of 0.1359 out of a total of 1. Or you can think of it as 13.59% of the total. Right? So we don't know what this problem refers to, but we do know that this probability is 0.1359. Excellent. All right. So now, by the way, if you have the TI Inspire, it's a much more powerful version of this calculator, but I actually don't know how to use it. So if you do have one, chances are you'll have to go to maybe a somewhat different menu to find what you're looking for, but it basically works the same way as the TI-84. Okay, so don't be concerned about it, but you may have to do some research on the internet to figure out how to access all of these functions. Well, all right then. Now, why don't we try another example? Now, this one, if you notice, we're looking at an area between 2 constants. What about a case like this? How about if I need to know the probability that z, and once again, this is the standard normal distribution, is greater than or equal to 1.5? Now, of course, if you remember that the normal distribution goes all the way up to positive infinity. So that means the upper limit in this case is in fact infinity. So you're looking for the area between 1.5 and infinity, but if you remember too, this calculator does not have an infinity button. So the workaround is to type second comma 99 and type it very carefully. When you do it correctly, you'll see in your window E99, which is the calculator shorthand for 1.0 times 10 to the 99th power. So that's not exactly infinity, but it's getting pretty close. So then, of course, you leave in the 0 and the 1 for the mean and standard deviation. And if you do this on your calculator, you'll see that rounded to 4 places, we're getting 0.0668. About 6.68% is under or in the shaded region. All right, so hopefully you're getting these numbers. If not, you probably made a typo somewhere. The infinities, make sure you are doing the keystrokes exactly as I'm showing them. Otherwise, you're going to end up with a mess. Okay. Now, why don't we get some experience with negative infinity while we're at it? Okay. So I'm going to reverse this. And this time I'm going to look for the area below negative 1.5. Let me write that in here. So on the left side of this distribution, of course, it's understood that it's going all the way down to negative infinity. All right. So when you go to normal CDF, the lower limit will be the negative infinity, which of course doesn't exist on the calculator. So what you're going to do is put a negative and then second comma 99. And if you do it correctly, you'll see in the window, it says negative E99, which means minus 1.0 times 10 to the 99th power. Okay. Then you put for your upper limit negative 1.50, and then you'll have a mean of 0 and a standard deviation of 1, because again, this is still the standard normal distribution. All right, so hopefully you're able to get the answer. And if you notice, interestingly enough, it's also 0.0668 or 6.68% of the total. So then you start to ask yourself, well, is this a coincidence? And the answer is no, because we have this wonderful property, as you recall, of symmetry, which means the right and the left-hand side are mirror images of each other. So based on that logic, it stands to reason that the probability of being above 1.5 equals the probability of being below negative 1. And they both in turn equal 0.66. All right. So in other words, if you had remembered that detail, you actually did not need to go to the calculator for this one because you already knew what was happening in the right tail. So you would have said, well, based on the symmetry of the distribution, the area below negative 1.5 must be the same, or 0.0668. Now, we don't always get that lucky with the problems we're given. I don't know how that's going to work out of MindTap, but if that does happen, you'll know what it has to be because of symmetry. And similarly, by the way, while we're on this topic, if you look at this example, let's see. I'm not sure if I have room to show this, but I'll just make a note here somewhere that this would also have to be 0.1359 because, again, of the symmetry of the distribution. So the area between positive 1 and positive 2 has to match up with the area between negative 2 and negative 1. Okay. Again, due to our favorite property in the world, which is symmetry. All right, so now we get how that works. Now, here's another thing we could figure out from all of this. What if I needed to know the probability that z is in between positive and negative 1.5? Well, again, we can take advantage of the properties of this normal distribution and do it with the calculator, of course, but using the properties. So in other words, if you come down here, you'll see that I plugged it into the calculator. I've got a lower limit of negative 1.5 and an upper limit of 1.5, the same mean and standard deviation, and it turns out to be 0.8664. Now, how do you know that? Because the whole area under this curve is equal to 1, which means that the unshaded area equals 1 minus the shaded area. Okay, or we could write it like this. 1 minus the area above 1.5 and minus the area below 1.5. So after I subtract those two, I end up with 0.8664. How do you like that? So, sometimes you can use these properties to help yourself come up with these probabilities, but of course you can always double check with the calculator. All right. So, in fact, it might be a good idea just to make sure. But between the property of symmetry and the fact that the whole area adds up to 1, that will really give us a lot of insights into how these probabilities work. Now, here's one that I think we mentioned this the other day. If you look under this standard normal curve, the mean is 0, which means the probability of being above 0 is 1/2. And the same thing is true for being below 0. Okay, and again, this is because of symmetry. So it stands to reason that if the whole area equals 1 and both halves each add up to 1, the only way that can happen is if each one is 0.5. Okay, so if you get all three of those, well, actually it's two, the symmetry and the fact that the area under the curve adds up to 1, you really will have a lot of key insights into how this normal distribution works. And it's only going to help you solve for these problems. Okay. Now, if you notice, all of these examples assume that we're dealing with the standard normal distribution. Now, of course, that's not always going to be the case. In fact, most of the time we'll be dealing with other normal distributions that have their own mean and standard deviation. What do we do in those cases? All right, so here's an example. Now, we've seen this one before. We have the scores on an exam are normally distributed with a mean of 80 and a standard deviation of 5. Okay. So first things first, we're going to use the letter X. We use Z only for the special case of the standard normal distribution. All the others, we use X. Okay. Think of the standard normal as like the royalty of the normal distribution family. Okay, so X will be our exam scores. X is normally distributed or normal with mean 80, standard deviation 5. With that being said, we'd like to know the probability that somebody gets less than or equal to a 70 on the exam, or 70 or less. So if you draw the picture this time, you'll put 80 in the center. Now the 70 is here. The 70 is actually the mean minus 2 standard deviations. So I'm going to write that here. All right, so yes, it is 70, but that represents being 2 standard deviations below the mean. Now you're going to go to your calculator and you're going to type second var, number 2, normal CDF. If you notice, once again, the lower limit is negative infinity, the upper is 70. Here's what you want to be careful about. You must change the mean and the standard deviation to the new values. If you forget, of course, you're going to get the wrong answer. So, we had a lot of cases with a mean of 0 and standard deviation of 1. And so it's easy to get into the habit of just leaving it at those levels all the time. But for this one, we have to remember to make the change. Okay, so don't forget about it. And by the way, if you do forget, you'll notice that your answers are either like crazy large or crazy small. And that's a hint to you that you probably have done something wrong. So you can go back and make the change. And if you do that here, you'll see that the final answer is 0.0227. 2.27% of the total area is to the left of that point. So that means there's a very slim chance of getting less than 70. All right. Actually, let me make this a little neater here. Okay. Now we're going to, oh, there it is. I'd already done this. Okay. All right. So far, so good. Is everyone getting these numbers with their calculators? Good. Okay. I'm just looking to see if there's any cool pictures in here. Sometimes people have little icons. Um, Sometimes it's just your name. Sometimes it'll say something like John's iPhone. I guess if you're signing in with an iPhone, it makes it clear that that's what you're doing. It looks like nobody's doing that here. Okay. Not like it matters. Um, anyway, so why don't we try this case? Oh, look what we've done. We've reversed it. It's again one of these cases where up here we have less than 70, less than or equal to 70, actually, two standard deviations below the mean. Well, guess what we have here? We have the other side of that. And of course, you can see that 90 is two standard deviations above the mean. So it stands to reason that you're going to get the same answer due again to our old friend symmetry. And that's exactly what happens. So if you type in these numbers, 90 up to infinity, second comma 99, you get 80 for your mean. Don't forget 5 for your standard deviation. And then that will in fact give you 0.0227. Okay, so they have to be the same. All right. Now, of course, we're not always going to get so lucky, but when we do, we want to put it to good use. Now, going back to what I was saying before about those tables, um, the thing is about the normal distribution is that there's actually an infinite number of possible normal distributions because you can have an infinite number of means and an infinite number of standard deviations. So you can't have realistically an infinite number of normal tables. So what the standard practice is to do this, have a table for the standard normal distribution. And if you have any other case, we have this special conversion formula, which takes any normal random variable x. Let's make this clear. X is normal with the mean of mu and standard deviation sigma. Whatever that is, if I subtract the mean and divide by the standard deviation, the result will be a standard normal random variable. So that means I can take any case and convert it into the standard normal case. And then by doing that, I can go ahead and use those tables. With a calculator, this is not such an important result, but when there were no calculators and there was only tables available, this was a huge deal. So when you do this, by the way, the resulting value is called a z-score. All right. So the word z-score means it's a number taken from the standard normal distribution, and the numbers you get refer to how many standard deviations you are away from the mean. Okay. So for example, a z-score of 1 means 1 standard deviation above the mean. Okay, so that's how you interpret these z-scores. They're telling us how far away are we from the mean. A z-score of, let's say, -2 means mean minus 2 standard deviations. All right, that's what I just want to remind you that that's how it works. Now, here's that exam question again. Same setup, mean of 80, standard deviation of 5. What if we now want to know the probability that our score is somewhere between 75 and 85? Okay, perfectly valid question. Now, if you remember, From the empirical rule, what we're looking for is the probability of being within one standard deviation of the mean. So remember, that's approximately 68%. When you pop this into your calculator, you'll see that it's actually 68.27%. Within one standard deviation of the mean is how we can interpret this. Okay. So now, what if instead, let's say it's ancient times and there's no calculators, there's only tables. What I can do is to convert this into the equivalent z-scores. And here's what we're going to do. We're going to use that same formula, x minus mu over sigma. And so because the mean and standard deviation are 80 and 5, we're going to apply this formula to both of these, the upper and the lower limits. And so you can see the x becomes a z. And so instead of having the probability that x is between 75 and 85, this is the equivalent to asking what is the probability that the standard normal random variable is between negative and positive 1. So if you plug those into your calculator, if you do this, by the way, don't forget to change it back to a mu of 0 and standard deviation of 1. And guess what? It's not a coincidence. It'll end up being the same thing, 68.27 or 0.6827. Okay. Wow. So, but now this is in principle not necessary if you have a calculator, but it's important to understand how this works. All right. So now here I've drawn a little graph. I'm hoping that this will help us understand this even better. On the top, we have the actual scores, which are normally distributed with a mean of 80 and a standard deviation of 5. On the bottom, we have the z-scores with a mean of 0 and a standard deviation of 1. And even though the graphs are not perfect, you can see that they're the same shape that they're supposed to be. So in the top, a value of 80 corresponds to 0 on the bottom. And 85 corresponds to 1 on the bottom, and 75 in the top corresponds to a negative 1 on the bottom. So in a way, what we're doing here is really no different than converting Fahrenheit into Celsius or vice versa. You're scaling the scores from the test into what are called standard units. Okay, so they both mean the same thing. Okay, so in other words, x being between 75 and 85 is the same thing as z being between positive and negative 1. Okay, because z represents the standard normal, x is normal but not standard normal. And so what really is different between the two is simply the units in which they're measured. That's it. Wow. All right. So think of that as our review. Now, if you go into the slides, they've got some problems waiting for us. And so let's skip ahead a little bit. So here's a case where, and again, we'll save the Excel for next time. So here's a tire company, and they have these new steel belted radials. They're going to sell them through a chain of discount stores, but they want to know the likelihood of the tires lasting a certain number of miles. So they're telling us down here that the tires are, the length of time that the tires last is normally distributed. The mean is 36,500 and the standard deviation is 5,000. Fine. All right, so I wrote that down here. So X is the mileage of a tire. X is normal, the mean of 36,500 miles, and a standard deviation of 5,000 miles. So they want to know the likelihood that a given tire that they produced will last at least 40,000 miles. Well, what do we do? So if you can imagine, this is no different than any of the other problems we've run into. We go to second vars, number two is normal CDF, and the lower limit is 40,000, the upper is infinity, which again, we express as second comma 99. And then, now again, we have to watch it. Make sure you change the mean and the standard deviation. Here we have 36,500 and 5,000 respectively. Don't forget. And so if you do that in your calculator, you'll see that you're going to get 0.2420 approximately. That means about a quarter of their tires should last more than 40,000 miles. Now, hopefully that's good news. I mean, that's what they wanted to hear, but all we know is that with these assumptions, that that's the correct probability. Now, here's the diagram, and you can see that, and they're actually going to ask us this question. How many standard deviations above the mean is this 40,000? That's something we haven't considered just yet. So far, we've only had like one or two above or one or two below. Where does that 40,000 stand compared to 36,500? So this is one time when this formula will come in very handy. What I have to do is I'm actually solving for X in this case. No, I'm not, sorry. I'm solving for a particular case of X, which is 40,000. The mean is this 36,500 and the standard deviation is 5. So if I plug in all these numbers, you'll see that 40,000 miles for the X scale is equivalent to 0.7 in the Z scale, or so in other words, the Z score is 0.7, which implies that this 40,000 represents being 0.7 standard deviations above the mean. Now, if you plug that into your calculator, you'll get the same number. You get that 0.2420. But if you wanted to double check, you could do this. Use 0.7 as the lower limit. Use infinity as the upper. But now make sure you convert the mean and standard deviation back to 0 and 1. And if you take out the old calculator, I'm going to do that right now. We have everything from 0.7 up to infinity, and then 0, 1, and what do you know? It's 2420. It's not a coincidence. How do you like that? Okay, so it's possible that MindTap will actually ask you to do something like this. So, it's a good idea to be ready for this. Now, they're going to come along here and throw a monkey wrench at us. Okay, be aware that there's going to be a monkey wrench heading your way. They're going to reverse this question on us. Imagine the company is saying, listen, we're going to offer a guarantee of some kind. And what we'd like to do is guarantee the public that if the number of miles they get falls below a certain level, we'll give them a new tire. Okay, so it's like a guarantee that you'll get at least X miles from your tire. But the way they're going to choose that value is they want to make sure that if they do have this guarantee, that no more than 10% of the customers will end up taking advantage of it. So in other words, what we're actually looking for is the lower 10% of this distribution. Okay, so here it is. We know that the mean is 36,500. And we know that the standard deviation is 5. So X, if you notice, X is sitting there. X represents the number of miles such that um, 10%, the number of miles would be less than X 10% of the time, right? But we don't know what X is. So one way we could go about this is to convert that X into a Z-score by, oh, it looks like I didn't do it here. So what you would do, you just want to make sure I'm following their approach. Um, they're saying that if Z equals X minus mu over sigma, algebraically, that implies that X equals sigma Z plus mu. Okay. So that means that we can solve this. The only thing is we still need the Z-score. So in other words, if you look at your standard normal curve, there's going to be some Z-score that corresponds to a left tail area of 10%. How do we find that? Well, I'm glad you asked. Now, this requires us to introduce a new function on the calculator. So if you go to your calculator and look at second vars, scroll down this time, not to number 2, but to number 3. And it's called INV norm, which stands for the inverse of the normal distribution. Now, if you go there, you'll see that it's only asking for, well, actually, there's 4 things going on here. We need an area of 0.10. Now, before we go any further, I just want to point out that even if you have a TI-84, you might have a slightly different version than what I have. You also may have a TI Inspire. So what I would like you to do right now is go to your INV norm function and go down to the bottom and see if it has this tail entry here. Now, if it's there, I would like you to make sure it's set equal to left. In other words, you slide it over there with the arrow key and then hit enter. If your calculator doesn't show this option, that means it is defaulting to left. So if we all set it equal to left, we're all now going to be doing the exact same thing. Okay. So if it's not there, just don't worry about it. If it is there, make sure that it says left. All right. Now, once that's been settled, the area, and you can see the purpose of this left command, 0.10 represents the left 10% of the distribution, not the right, not what's in the middle, but the left. And if you plug in those numbers that you're seeing there, of course, remember, this is the standard normal. So 0 and 1 are the mean and standard deviation. You should get approximately negative 1.28. And so that means that this area, which I alluded to here earlier, this area of 10% corresponds to a z-score of negative 1.28, which in turn can be interpreted as 1.28 below the standard deviations below the mean. Now we can calculate the answer to our question. So remember this formula I derived for you up here. So for what we're trying to accomplish here, Z is negative 1.28 because we're trying to find the boundary with the lower left 10% of the distribution. The sigma is the same one we had before, 5,000. And the mean was 36,500. Or you can rewrite this as 36,500 if you're more comfortable with this. And any way you look at it, you're going to get approximately, using this approach, 30,100. So what this means is that if the company guarantees that a tire will last at least 30,100 miles, only 10% of the customers will be eligible for a replacement tire. And that's what they're hoping. I guess they're figuring, well, we could have a ridiculous guarantee like 0 miles, but nobody would buy our tires. So we're going to have a realistic guarantee here. We're saying, listen, reasonably, you can expect to get at least 30,000 miles out of this tire, 30,100. If not, bring it back and we'll give you another one. And otherwise, people won't know whether they can buy this tire or not. Now, of course, if they're going to advertise this, they're going to have to be prepared to prove this to the FDA with their numbers. They'll have a statistician somewhere who's saying, listen, here's what we found, and is ready to be able to back this up, okay, in writing and say, listen, here's how we came up with this number, 30,100. Otherwise, they're asking for trouble. Now, it turns out that there's a quicker way of doing this, though, that we could have used, but you never know what MindTap is going to ask you to do. So I decided to show it to you both ways. All right, if you don't mind. So the other approach would have been to do this. Don't even bother with the Z-score. Just go ahead and do it directly. Okay, so you go back to your second VAR's INV norm, type in an area 0.1 with the understanding that that's the left area, the left tail area, type in the mean and the standard deviation, and except for some slight rounding differences, you're going to get the same number. And it's actually before we got 30,100. But that's because we've rounded. This 1.28 is rounded. This number is the actual number, 30,092.24. So either way, you'll get approximately the same number. Okay. Wow, that's a lot. I mean, for the Friday before spring break, this is a lot of material, and I get it. And we'll be doing this again on Tuesday when we get back, except we'll also be doing a lot of Excel. Now, since there's a few minutes left, I would like to at least briefly introduce what's coming next. Now, let's go back to the slides for a minute. And I did remember way back in the beginning, we said that in this chapter, we'll have 3 different distributions. The uniform, which we're done with, the normal, which we're sort of done with, but we'll never actually stop using it. And then the exponential. And you can see what an interesting one this is. Look how that tail goes down forever. So anyway, let's at least start to introduce this one so that when we see it again, when we get back, it won't be completely new. Okay. All right. So like the other two, what uniquely characterizes the exponential distribution is the formula that we use to calculate its probabilities. And here it is, okay? This formula represents the probabilities for this distribution. But before we look at this, what I'd like you to do is think about what this distribution is for. Now, it turns out that it's closely related to the Poisson. Now, remember with the Poisson, we use it to figure out the likelihood that a given number of events occur over a given time interval. For example, what if we know from historical experience that on average there are 8 customers coming in this store every hour? That means we can figure out the probability, let's say that 5 customers come in the store in the next hour, or 2, or 3, or 8, or whatever the case may be. Here we're flipping it around though, Instead, we want to know the probability that a certain amount of time will pass until the next customer shows up. So we might ask questions like this: what is the probability that it will be 10 minutes before the next customer comes in the store? That's what we're going to do with the exponential distribution. So if you look at the formula, you'll see some familiar elements. The mu is the mean, and I'll make a note here, same mu that appears in the Poisson formula. Okay. And then, of course, here's our old friend E, which we've seen before in the Poisson distribution, and it's a constant that's approximately equal to 2.7828. Now, one way in which this one is different than the others is that if you notice, this one is only defined for positive values of X, or I should say non-negative. That wasn't true for any of the other ones that we've seen so far. But this one, it starts at 0. And it looks something like that. Okay. So, and because this is a continuous distribution, we can only calculate probabilities for intervals. Like, for example, we could calculate the probability that the next customer arrives between 10 and 15 minutes in the future. The probability of arriving at a specific time, like 15 minutes, is defined to equal 0. Now, here's some bad news for everyone. The exponential distribution does not appear in our calculators, or at least not the TI-84. If you have the Nspire, it's possible that it's there, but I don't know that for a fact. Luckily, it does appear in Excel. So what it does not, so that means we have to actually calculate these probabilities directly from this formula, but it's not that bad of a formula. I mean, really, look at it. The only thing we have to watch out for is this. We must be careful with the units. For example, if the mean is defined as 8 hours, or 8 per hour, then the probability that the next customer arrives between 10 and 15 minutes would have to be written as that the next customer arrives between 1/6 and 1/4 of an hour. Okay, so that would be the one thing I would like to mention here, although we'll see it again next week. So now this is about where I stopped with the other class, the 8:30 class, I mean, because, well, there's a lot of material, but also not everyone's here. And I don't want to get too far ahead. So what I'd like to do is stop right here. Now I'm going to post a recording as well as this document. The recordings will be available both in Blackboard and in my YouTube account, which I think I showed this to you once before. The reason for doing that is because sometimes, these videos can swallow up an awful lot of space. Okay. So this is my account, Dr. ACA. And if you look in here, you'll see, let's see. I've got playlists here for a lot of classes I've done in the past, and there's a lot of them. Ooh, look at them all. But the thing is, ours is right. Well, I'm going to create a new one just for us. It'll say Econ 2140 1130 Spring 2025. That way you'll know exactly where to find your video if you want to look for it here. Otherwise, you can just go find it in Blackboard. Okay. So yeah, this is the one I did this morning for the other class. All right. Well, anyway, I think that's enough fun for one day. Now, I'm not going to see you for a long time. So when we get back, we'll go through a quick review of what we did here, and then we'll start learning some Excel commands. And then, like I said before, we have to start thinking about a schedule for reviewing for the second midterm and a date for the second midterm, which is based entirely on chapters 4 and 5. Okay, now this is 6 that we're looking at now. So clearly we're ready for the second midterm. We just have to decide when to have it. All right. So other than that, I think we're all set here. If you have any questions, you can send me emails. I'm still working on the midterms. They should be ready by tonight. I'm hoping to get that grade book set up. And as usual, if you're dying to know your score, you can send me an email too. But one way or the other, you should know by late tonight or first thing tomorrow. Okay, so hopefully you have a great spring break. Okay, and I'll see you all a week from Tuesday. All right, bye. Okay, you're welcome. Bye.